Hello, my dear students. So, I would like to take this opportunity to apologize if I am not around in your class today. But nevertheless, even with my absence, rest assured that you will be learning a lot of things despite my absence. So, if you are planning to leave the class right now, well, you will be missing half of your life. So, sit back there, go back to your seats. Don't transfer to any other seats. Take your notebooks with you and write important notes because I will be sharing to you a very important lesson that you need to learn for this week. So, what are you waiting for? Sit back, relax, and learn. Refraction is the bending of light rays as light passes obliquely from one medium to another medium. Let me tell you just one thing about refraction of light. Take note that refraction only happens if white light or light itself passes obliquely, that is, light passes at a certain angle to the surface of any transparent material. Now, this bending effect happens because as light passes from one medium to another medium, its velocity or its speed abruptly changes due to the differences of the properties of these media where light is passing. Now, refraction happens primarily due to one of the properties of the materials or medium where light travels, and that is its index of refraction. Now, the index of refraction is a number given as the ratio between the speed of light in vacuum and the speed of light at a certain medium. You have to remember that the speed of light in the vacuum is given as the value of c, where it's equivalent to 3 times 10 to the power of 8 meters per second. Now, as what I've told you from the previous presentation, light, as it passes from one medium to another, it changes its speed, and that is because of the index of refraction of the material. Now, the index of refraction of a material is given by the formula N is equal to c over v, where c is the speed of light in vacuum and v is the speed of light at a certain medium. Notice that the value of n could not be equal to 0, or that n could not be less than 1, since the speed of light is bigger than that of the velocity of light at a certain medium. That is, c is always greater than v. So, it is very important to note that the index of refraction of light, or material rather, will not be less than 1. Okay? Materials exhibit different indices of refraction due to the fact that they have different densities. Now, why did I say density? Well, it's because the density of a material is primarily linked to its index of refraction. So, when I say it's primarily linked, that means it's certainly dependent on the density of the material. So, what's the implication? The higher the index of refraction of a certain material is, then the greater will be the density of that material. So, high density is equal to high index of refraction. Now, the index of refraction of a material is given on the table you're seeing right now on the screen. Notice in the formula given a while ago that if we divide the speed of light, or c, by the number itself, you will get an index of refraction which is equal to 1. Now, if this value slightly changes, then our index of refraction will always be greater than 1. Take a look at example for air. Now for air, you notice that the value for index of refraction is very close to 1. That is why in our calculations that we will do later, we will always assume that the index of refraction for air is equal to 1, or n is equal to 1. This means that we assume that in air, the speed of light does not change compared to when the speed of light is in the vacuum. And the rest are given already on the table. So always remember that you don't have to memorize these indices of refraction, because in our problems later, these are always given as part of the problem. So don't bother yourself about it. Okay? Now we have answered as to what is refraction. Now the only question that remains, or maybe what's bothering in your mind right now, will be, why is refraction happening, or how does refraction happens? Now, I want you to take a closer look at the explanation that I'm going to provide in the next slide. Okay? As explained in our discussion a while ago, refraction of light happens when there is a bending effect when it passes from one medium to another medium. And this is due to the fact that these two media where light passes through have different properties. So, how does white light bends in this case? So before we're going to explain, let's first take a look at some of the important terminologies that you can see right now on the diagram. We have our normal line here, which is just an imaginary line, an imaginary vertical line that runs through our surface. And then we have N1, N2, which basically talks about the index of refraction. So the index of refraction in this case is somewhat directly related to the density of the material, because the greater the density of a material, the tendency is the index of refraction also gets bigger. So I want you to remember that one, okay? The greater the density of the material, the greater the index of refraction. So let's take case number 1, for example, wherein N1 is less than N2. This means that our N1 is less dense and our N2 is denser in this case. So how does white light behave or refract in this manner? So from our illustration here, let's imagine that an incident ray coming from medium 1 passes through another medium, which is your N2. Now, because N2 has bigger density than medium 1 or N1, the tendency for this light is to bend towards or closer to the normal line. Okay, is that clear? Again, when it passes from the incident ray from medium 1, your light rays refract towards our normal line. So I will call this blue line as the incident ray and your red ray as your refracted ray. So if you notice this angle here, which is our angle of incidence in this case, or angle 1, you notice that the size of our angle 1 is actually bigger than our angle 2. So this means that if white light bends from a less dense, which is N1, to a denser medium, or N2, our angle of incidence becomes bigger than our angle of refraction, or angle 2. So what is the implication right now? This would only tell us one thing, that if white light enters from a less dense medium, or N1, to a denser medium, or N2, white light travels slower. Let's take a look at another case. For example, let's make N1 bigger than our N2. This means N1 right now is denser than our N2. So what happens when light enters from a denser medium, again, from a denser medium to a less dense medium? So you notice that the incident ray, when it passes from N1, you will notice that our refracted ray in this case is bended away or further from our normal line. So what happens right now to the angle of incidence and to the angle of refraction. Now, I don't need to ask you because it's very clear based from what you can see right now on the diagram. See, you notice the difference? Angle 1 is what? No, it's not bigger. Angle 1 is actually smaller than angle 2. See that? Yeah? What? Alright. Now, what is the implication of this happening or phenomenon rather? Sorry. You will notice that if white light travels from a denser medium to a less dense medium, it actually travels faster. Meaning to say, when it enters from medium 1 to medium 2, light rays travel faster compared to the previous medium. And this is how refraction happens in a nutshell. The refraction of light can be mathematically expressed using what you call a Snell's law of refraction. Well, technically it's called Snell's law of refraction. It's because it's named after someone who's named Snell. I don't remember the name, but we don't bother with the names, we bother with the calculation. So there's no need for you to memorize the name of that person. So what does Snell's law of refraction tell us? Well, the Snell's law of refraction tells us many things, like how light refracts and what are the factors that affects the refraction of light. Now, this event, what we call as refraction, are described mathematically in these equations. So the first equation that we're going to look at is the relationship of the incident angle and the refracted angle in relation to its indices of refraction. It is given by the formula n1 sine angle 1 is equal to n2 sine angle 2, wherein n1 is the index of refraction for the first medium, angle 1 as the angle of incidence, n2 as the index of refraction for the second medium, and angle 2 as the angle of refraction. The second equation tells us about the relationship between the angle of incidence and refraction to the speed of light in the first and second medium. So, Snell's law of refraction can also be interpreted as sine angle 1 divided by v1 is equal to sine angle 2 divided by v2, wherein, of course, angle 1 is our angle of incidence, v1 is the speed of light in the first medium, and angle 2 is our angle of refraction, and v2 as the speed of light in the second medium. Notice that in these equations, you will somewhat have the idea in mind that the speed of light actually changes when it passes from one medium to another medium. And in fact, from the formula itself, you can see that the angle of incidence and the angle of refraction is actually affected by how light travels or how fast light travels in a particular medium. Let's synthesize further about Snell's law of refraction. But before we go to the mathematical calculations that is involved in this law, let me just tell you that Snell's refraction tells you only one thing. That means that light refracts in a way that is affected by several different factors, and that includes number one, the index of refraction of the material, and at the same time, the properties of the different media where white light is traveling. So, as an effect of these factors, there are several variables that are affected during white's light. Balik. Synthesize everything regarding Snell's law of refraction. But before we go to the mathematical calculations of this law of refraction, let me just tell you that this law tells you one thing, and that is light refracts in a way that is affected by number one, the index of refraction of the material, and of course, the different properties of the media where light travels. And as a result, white light, when it enters from one medium to another, can either become faster or travel slower. And this phenomenon is perfectly described in these mathematical equations. First, let me write the first equation for Snell's law of refraction. This tells us that in relation to the angle of incidence and angle of refraction, n1 and sine angle 1 is equal to n2 sine angle 2. Now, this equation tells you one thing, that the angle of incidence and the angle of refraction in this case is dependent on the indices of refraction of the media where white light travels. So, let me define some variables here. N1 is of course the index of refraction of the first medium, and N2 as the index of refraction to the second medium. And angle 1 is of course our angle of incidence, and angle 2 is our angle of refraction. And we know that sine is a trigonometric function, which we will be using later in our calculations. Now, another equation that would help us describe further the behavior of white light in relation to its velocity is perfectly described in this equation. Sine angle 1 over V1 is equal to sine angle 2 over V2. So, let me define further these variables. We know for the fact a while ago that angle 1 is our angle of incidence, and angle 2 is our angle of refraction, and that V1 here is the speed of light in the first medium where it travels, and V2 is the speed of light in the second medium where white light exits or travels. So later on, we don't know yet whether from V1 to V2 it becomes faster or slower. So we will know the significance later of these equations later on. Now, if we are going to synthesize all of these equations and combine them in order to form another equation, we'll be able to find out that actually this Snell's law of refraction tells us that the behavior of light as it refracts from one medium to another medium is dependent on the index of refraction as well as to the speed of light from the two media. And if we combine these equations right now, it can be N1 V1 is equal to N2 V2. This tells you that the speed of light from one medium to another is dependent to its indices of refraction. Our problem posted on the screen a while ago, it is asking you what is the speed of light in the second medium. So how do we step by step solve this problem? First, always remember, always write what is asked in the problem. And what is asked in the problem is your V2. Okay? Or the speed of light in the second medium. And in our problem, there are variables that were given. Number one is we have N1 and we have N2. N1 is of course given as air with an index of refraction of 1.00 or 1 in simple sense. And then N2, which is your glass, given as 1.51. Now, if you have read the problem is assuming that the speed of light in the first medium is equal to the speed of light in the vacuum, or we call it as C. So we write here V1 is equal to C, which is given as 3 times 10 to the power of 8 meters per second. There. So, we are asking right now how to get V2. So, we write the solution here. Are you following? You should. So, our solution here will be based on the given variables itself. You will know right away what equation you are going to use. So, in this case, we are going to use the third equation that we just introduced since the given variables are only v and n. So, the equation goes n1 v1 is equal to n2 v2. There. And substitute the variables. This is 1.00 and v1 is 3 times 10 to the power of 8 meters per second is equal to our n2 is 1.51 times, and v2 is unknown, so we write it as an unknown variable. Of course, 1 times 3 times 10 to the power of 8 meters per second is just the same. 3 times 10 to the power of 8 meters per second is equal to 1.51 times v2 is 1.51 v2. Now, to get the value of v2, all we need to do is just cancel 1.51 by dividing the whole equation by 1.51. Okay. Cancel this so that v2 will be isolated. So, our calculated value for v2 will be, punch your calculators right now. You done? Actually, you don't need a calculator to do this. You can just do this mentally if you're good in math. But if you're not confident, then rely on your calculator for the time being. So, you will find out that you're going to mentally calculate it. 1.51, 3 times 10 to the power of 8, of course, that's 1.51. So, I'm assuming that the value is close to 1.98 times 10 to the power of 8 meters per second. So, this means that the speed of light in the second medium is 1.98 times 10 to the power of 8 meters per second. Or, you may find out that in your calculator, it is given as a whole number, around 1,900,000 something. So, I don't know what's the exact value, but I'm just assuming that this is the answer. But, just kindly please correct whatever would be the answer, because I was just mentally calculating it in my head. So, it will be your job to correct if this answer is right or wrong. But the answer is closely approximately 1.98 times 10 to the power of 8 meters per second. Now, how do you check if your answer is logical enough? So, if you're going to look at n1 is 1, right? And n2 is 1.51. We just discussed a while ago that if n1 is less than n2, it should be that the speed of light in the second medium will become slower. And since our answer is smaller than the initial speed, which is 3 times 10 to the power of 8, that makes our answer logical, because indeed, our second velocity in the second medium became slower. Now, problem number 2 is telling us that white light was traveling from ethyl alcohol to water at an angle 35 degrees. Now, the problem is asking us what should be the angle of refraction in this case. So, how to solve this problem? First, always write what is asked in the problem, and in this case, what is asked is our angle of refraction, or angle 2. Now, always write the given variables in the problem. So the given variables are n1 is equal to 1.36, that is for ethyl alcohol. And then we have n2, which is 1.33. And of course, we have our angle of the angle of incidence rather is 35 degrees. Now, how will you know what equation are you going to use in this problem? Now, the first thing that I should always look at every time I solve problem is that I always check what are the given variables in my problem. So in this case, what is given are the n, or the index of refraction, and the angles of incidence and refraction. So the only equation that contains these two variables is, of course, if you're going to check it right now, is what equation? Yes, it's equation number 1. So we use equation number 1 in this case. So we write sine angle 1 is equal n1 is equal to sine angle 2 n2. Then replace the variables in the equation. So sine 35 times 1.36 is equal to sine angle 2, which is unknown, times 1.33, because that is for water. Now, simply input sine 35 in your calculator if you have a scientific calculator right now, and then multiply it directly to 1.36, and you will get the value of 0.7800639,534. Now, don't round up your answers here, because if we round up our answers here, we will have an inaccurate answer later in our final answer. So we only round up in the final answer, and then 0.7800639,534 is equal to sine angle 2 1 times 1.33. Now, to isolate sine angle 2, you have to divide the whole equations by 1.33, and then if you do so, sine angle 2 will be equal to 0.586514250. Again, you have to write the whole thing, which is equal to sine angle 2. Now, this is not yet your angle. This is still the value for sine angle 2. Now, if you want to get the angle here, you have to have the reverse function of the sine angle 2 here. So to do this, don't touch the results of in your calculator right now. Now, if you have the results in your calculator right now, just directly press shift in your calculator and then press sine. Again, press shift and then press sine in your calculator. And once you do that, press the equal sign and you will have the result, which is equal to 35.91 degrees as our angle of refraction. Now, how do you check if your answer is logical? You have to note that in our problem is that n2 is less than our n1. So we expect that our angle 2 must be greater than angle 1 based on the discussions that we had a while ago. You get it? Alright. Rock and roll the world. Woo! Now that I have shown you how to solve problems involving Snell's law of refraction, it is now your time to solve these two problems that I am posting right now on the screen. Now, I want you to do this on your own, okay? Now, if ever you have some questions regarding the calculations for the Snell's law of refraction, you can always replay the video or the presentation that you had right now. And right after, if you are confident that you have really solved the problem, you can always check the solutions for the problem by logging into your account in the NGS. Just click geometric optics, or rather, first click on my subjects and then go to my subject, science. Then once you have logged into the subject, just click geometric optics and click answer key to sample problems. In there, you will see the details of the solutions that I have written for the problem. But remember, don't look at the solutions yet if you have not yet performed the problem. Okay? Well, God bless, and may the odds forever be in your favor.